One type of improper integral involves infinite discontinuities. Notice this integral. We've got this integral from 0 to 1. Now, a lot of times we think of improper integrals as having infinity in the limits of integration here, but this one doesn't. This one just goes from 0 to 1, but you notice that what makes this an improper integral is the fact that 0 is in the lower limit here, and that will make this undefined. Notice we would be dividing by 0. In other words, there is a vertical asymptote at x equals 0, an infinite discontinuity. Well, that tells us that is one of the types of, we classify that as an improper integral. Now here's the way we deal with that one. We're going to rewrite this using a limit. So I'm going to take a limit, and I'm going to replace the 0 with an a. I just like using a here and b up here when I need to. But I'm replacing this with an a, and I've still got, everything else is the same, but I've got a limit. And what I'm going to do is I'm going to let a go to 0. But notice that the region that or the interval that we're dealing with starts at 0 and goes to 1. So 0 is on the left. So I'm going to need to say a is approaching 0 from the right. So if you consider this interval, if you're anywhere in this interval and you want to go to 0, you're approaching from the right. So I put a plus there. Okay. So these are typically going to be one-sided limits. Now, we've got to evaluate this. So here we go. We've got the limit as a goes to 0 from the right, the integral from a to 1. So this is x to the negative 1/3 power. Okay. I'm all set up to use the power rule for integration here. So here we go. We've got the limit as a goes to 0 from the right. And now I'm going to go ahead and do my antiderivative. I've got negative 1/3 plus 1, x to the negative 1/3 plus 1. And I'm going from a to 1. Here we go. Okay. Now we just keep going with that. We've got the limit as a goes to 0. And this is going to be 1 over 2/3 x to the 2/3 from a to 1, which of course 1 divided by 2/3 is just multiplying by 3/2. So here's what we've got now. We've got the limit as a goes to 0 from the right of 3/2 x to the 2/3. So I'm just being careful here. And now I just plug in. So I'm going to plug in a 1 here. And so here's what we've got now. I plug in the 1, and I've got 3/2 times 1 to the 2/3 minus the limit as a goes to 0 from the right of 3/2 a to the 2/3. Well, as a goes to 0, this whole thing here goes to 0. So really what we have here is 3/2 as the answer. Now for this problem, we had the discontinuity at the end point here of the interval. We were going from 0 to 1, and we had the discontinuity at 0. But that's not always going to be the case. In other words, our discontinuity can occur at other places. Let's suppose we have an integral from negative 1 to 2, and let's suppose it's dx over x cubed, like that. Okay. Now, you notice, so we're going from negative 1 to 2, and our discontinuity occurs at 0 when x equals 0. So that's inside here. So here's what we need to do. Here's the way we deal with this. We're going to split this up, and we're going to go from negative 1 to 0 dx over x cubed plus 0 to 2 of dx over x cubed. See? So I split it up so that the discontinuity does occur at the endpoint. I just split it up where the discontinuity occurred. It was at 0, so I went from -1 to 0, and then from 0 to 2. Okay, so let's see how this would work then. So we've got the limit here. The limit as, I'm going to do this, I'm going to say b goes to 0. Now, I'm going to modify this in just a second, but I'm going to go from -1 to b, x to the -3 dx. Now notice, we're starting over here at the left and we're going to 0. So we're approaching from the left here. See, so it's a left-hand limit. Okay, so be sure you understand that. See, okay. Then we have the limit as a goes to 0, and I'll fix that in just a second. But we're going from a to 2, x to the -3 dx. Now notice this time we're approaching from the right. A is on the left-hand side of the interval and 2 is on the right, so we're approaching from the right. Now what we've got to do is just evaluate these two integrals, these two improper integrals. Now both of them, let me just get the antiderivative first. The antiderivative is going to be -1/2 x to the -2. So if you just go through there and find the antiderivative, that's what you would get. Now, let's look at both of these. Okay, so for this one, this first one, I've got the limit. Okay, I've got the limit as b goes to 0 from the left of -1/2 x to the -2 from -1 to b. Okay, so that's this one here. Now this one over here, it's going to be the limit as a goes to 0 from the right of, same thing, -1/2 x to the -2 from a to 2. Now let's go ahead and evaluate these then. So if you look at this one here, okay, so let's just plug in here. We've got the limit as b goes to 0, and this is going to be -1 over 2 b squared. See, I just dropped the x down there, and I'm letting b go to 0. Okay. Minus a -1/2 -1 to the second. Now let's think about what we have here. This one, of course, no problem. This is just -1 over 2. Put it with this is just going to be 1/2. This part of it's 1/2. However, notice as b goes to 0, this part is going off to infinity. Okay, so this part diverges. Well, if that part diverges, in fact, I guess it's going to negative infinity, right? As b goes to 0 from the left, yeah, it's going to negative infinity. The point is, this thing diverges. Now, if any part diverges in this process, we say the whole integral diverges. So this integral right here, yeah, it diverges because this part of it diverges. So we're done with this problem. I mean, we could go over and, work this out and see what happens here, but we don't need to. As soon as we find one part diverges, the whole thing diverges.